So welcome everybody for this JVM meetup. Our main guest is arriving at any moment. In the meantime, they have a little challenge, which is to do a live code review of a small project I tried to do. This project is a ZIO watcher. It's a file system watcher, and I'd like to show you the main API, how it looks like, and then how it looks under the main implementation, and I'd like some feedback, some live code review. If it sucks, it sucks. If it doesn't suck, it sucks anyway. So let's try. So the main object is watch.
Can you turn the presentation on so it's better to see?
Do you have it? Yeah. Okay. They don't teach this at school, man.
Yeah, no. I will teach you now.
That's
Second from the bottom. Offer.
nice. Is it good? Yeah? All right. So, all right. So I was saying we have this main ZIO watcher, and it only has one method where you pass the path which you want to watch on the file system for changes, and this makes changes on the file system recursively. So it goes from top down, and the main once it completes the watch, it initiates the watching. It gives us a ZIO stream of events, and then events have its own type of what kind of events we can watch on. So now I need to go back to my files, man. How do I? Like this? Okay, we can try that. So yeah, sorry. So this is the interface. That's what we get. We can choose what kind of events you want to listen on. The modifiers is a NIO thing that lets you decide how sensible you want to be watching the file system. And then we have a pull timeout to look for changes. This is needed because ZIO streams, firstly, is how it works, the watch service for Java NIO. And secondly, ZIO streams is pull-based, so we need to pass it. And then we can check the implementation. No, I don't want to commit. It's all right. I'm getting started at this. Is no problem. I'm not shy. So. What we have here in the constructor, which is we have the service, which is a JVM thing. We have a ZIO ref, which allows you to atomically update your state, and just a log writer from log.effect. So it's a very nice way of doing things. We have the default event types, which we care about. In the constructor, you can also pass events that you don't care. Yeah. Just here we check for if it's a directory, because if it's a directory, we have to apply different semantics, like apply the recursive mode, and if it's a file, we just check the single file. Once we complete the instantiation of the watch, we pipe it through a series of method events that will start streaming the events to the user of the library. Here I'm depending on the blocking environment. Is it called environment, the blocking? So because here we are actually doing I/O, so I'm blocking using the ZIO blocking okay, so this registrations is my ref, my atomically, my map, which can be updated atomically, and when I initiate the track, I register into my map, my refs map. So once again, I am using blocking here because this creates some I/O. This is a console to watch. So when you instantiate a watch on the file system, it gives you a key, and you can then, when you need to finish the watch, you just call cancel on it, and I wrap it in a UIO because this is added to the registration object. So here is a bit more meat. So it's just simple is traversing the directory for children and adding it to my paths. Then here this is interesting, which is takes a list of ZIOs and it compacts it down to a single one, sort of traverse, but not really. Yeah, so here is where I create my registration by giving it the path, which comes from the traverse tree, the types here. What is that? I forgot. Skip it. Yeah, is what type of events you actually want to listen for. Modifiers is again those JVM watch events. And here, because it's directory, we say to recurse and to go down on the tree. And again, and then finally, I assign to the cleanup in my object the UIO of which does the cancellation. So nothing is executed at this point. So the watch file is almost the same, with the difference that we don't recurse. And we actually check for the path there. So this console registration was a bit tricky for me in a way because I wasn't sure how to do finalizers at the end of a stream, because I don't think you can interrupt a stream. Maybe you can, but I'm not sure. So I just go through my registrations, and then I updated it with after I cancel and clean up here. And here I have a to-do, which is a question I have, because the logger I have, it's only works on a task, not on UIO, and we cannot. When you finish a stream, the finalizer expects a UIO of unit. So here I still didn't figure it out. How can I log with a logger that depends on task? And how can I log it at the same time close everything at the end, which I'll show you in a second. Yeah. So this is the event. Once again, I'm just assigning a task here where I use the Java API for calling the pool. So the Java API needs this to be waiting on, to be pulling for changes on the file system. And then the important thing here, we have to call reset once you get events from the JVM. So this stream is a ZIO stream, and it's like similar to FS2 in the API, but you can repeat the effect. So I'm constantly calling for any changes on the file system. Then we collect the result. We zip it with we make a tuple out of it with our active registrations, which is in our state, and then we make a diff. How do we diff it? We diff it by checking the predicate and this is instance of. I didn't find a way to do it without it, because we only want the created events for this predicate. And then we return a stream from our list of filtered events, and we run forever. And this will just keep running. And here, this ensuring is what I was mentioning, that expects a UIO of ZIO UIO, and I didn't figure out yet how to do the logging, because the log library expects a task, because it actually does IO. Yeah, so that's the basics of it, and then we have some constructors. Just take the watch to create our initialization here, and yeah.
Well, I'm wondering, the watch service, do you need to close it somehow, or is it just like, because to me it's a bit suspect that there is no like closing of the watch service.
Yeah, I know you said that before. I have it on my to-do,
Okay.
and I used to have it, where is it? Watcher, and it should go here. Here is where I will add that logic with like this one.
Yeah. That one you need to close, right?
Yeah.
Does it make sense to actually close it here? Should it be closed
Like the color fixing.
yeah, in the color?
So the caller would be responsible for closing it, but it doesn't sound like a good API.
Maybe I'm asking wrong, but sorry, does it make sense to recommend not watcher but managed of watcher? That's like the analog resource from Capsify?
Yeah, that's my point.
Yeah.
Yeah, that's not so difficult.
Like
Passing the service from outside, so it goes outside also.
Oh yeah, of course, yes. That's right.
it's true, but then how could I offer this API for different types of constructors? It would be just like, if you pass me a watch service, then you are responsible.
So what I would expect from after like that,
But if you just call watch, I am responsible.
Yes.
yeah, I get, yeah,
Essentially, yes.
you are
Yeah?
responsible for creating this watch service, but you return like manage or something that does the coding.
Yeah. Basically, what you create, you're responsible.
Okay, that sounds great. It's good. Thanks. That's why we did this, so I get some inputs. So, a couple of things I learned along the way from the ZIO hackathon. One of them was from Thomas. Was because before I was doing ZIO dot for each, and then pass my list of ZIOs, and then I was. But it's better to show default. So that's why it's good to go to these hackathons. You learn this stuff. Where was it? Not for each here, but yeah, that one. This one. So before I didn't know, and I had this, which was really ugly. See? Something like that it was. And Tomasz told me the sequence method, which is really nice. Anyway, it was very nice to... Yes. Was that one, yeah? It's not my fault, it was Scala FMT. Or was it flap mat? No, it's not that. Anyway, it's just cool that you have different methods like sequence, traverse, all of that. And with a few lines of code, you have some nice, complicated, good-looking thing to impress your boss. Okay.
How long did it take you to create some things?
2 days.
Okay.
Like between train trips and stuff.
And it was your first CIO project?
Yeah, it was after last week. But I must confess, guys, I stole a bit from FS2 Stream's watch service. Just don't tell anybody. All right. So thank you guys for listening and watching my project. Any feedback, just check it out. Ask me, and I will probably merge your commit. Thanks.
All right, cool. So first of all, thanks for your patience, and thanks to our colleagues, Joao, Tomáš, and Honza, for coming up with impromptu presentation about personal projects. I think it's cool. We've just been to ZIO hackathon, so we all feel hyped, and we all willing to use the library, play with it a little bit. Nevertheless, the topic of our evening is going to be slightly different. We're going to talk about SchemaZ, which is library I'm personally not familiar with, but Valentin Kasas is a big contributor and has something to say about schema generation, schema evolution, and how to essentially use it in a meaningful way that saves you a lot of typing. And yeah, there are several use cases, like generating SQL queries to a database that adheres to a certain schema, or serializing data serialization. I think there's a big application in big data space, etc. So once Valentin gets set up, we hear from him, and yeah, I think it's going to be interesting. Thank you very much, and when Valentin is ready at his own time. Thanks.
Can you hear me? Yeah? Cool. Well, first, thanks, Tomáš, for the invitation. It's a great pleasure to come back to Prague. And also sorry for the delay. Apparently, every single flight I take this year is delayed by at least 30 minutes. So I should have known better, but anyway. So tonight I will be talking about schemas and schemas evolution, which is probably very obvious when you look at the title on the screen. Right? Sorry. But yeah. Before doing that, I would like us to ask ourselves a small question, which is, what is functional programming good for? And to me, there are two major answers to that question. First, functional programming gives us many, many cool tools for modeling complex data models. We have algebraic data types, we have pattern matching, we have immutability by default, and all that kind of good stuff that helps us define very precise domain models. We can use refined types, etc., etc. Another part where functional programming is very good is for modeling effects. And in Scala, we are very, very well equipped with good models for effects. We have ZO, Katz effects, monics. We can even use futures if we want. We are very well equipped to talk about effects and effectful computations. But, so, sorry. So in the end, we could say that we conceive our functional programming applications as tiny little boxes where everything we put inside is supposed to be pure, and everything that is not pure is supposed to be pushed as much as possible to the sides of the boxes, like side effects, right? But the problem is these boxes on their own are completely useless. We need to get data inside or data outside these boxes to make them useful in the real world, right? And therefore, all this nice and pure way of representing data inside our applications escapes from it through serialization, user input, and so on and so forth. And that's where the problem begins. Because in every project, we end up needing to write manual code to serialize data in many formats, like JSON or Avro, protocol buffers, Thrift, probably 3 other flavors of JSON, because why not? But also for validating user input, or for reading configuration files, or for accessing data stored in database, or for generating random data for our property-based tests, or pre-printing, comparing values, etc., etc., etc. And that's a lot of code we need to write. And this code we write in every single project is completely mechanical, repetitive, brings absolutely no business value. There would be no business value if that code wouldn't be written, but that code itself brings no business value. It's not that the value. The value is the model. The value is the behavior, but not how to serialize it, how to read input, data input, and so on. So we need to find a way to do better, right? Because we don't want to spend time writing no-value code. So, especially in the Scala world, the first idea we get when facing this kind of problem is, let's derive all that crap at compile time. And we have plenty of solutions for that. We have shapeless, we have plain old macros, Magnolia, SchemaZ deriving, and so on, that are generic solutions for generating this kind of code. And we also have specialized libraries like Codex, Cersei, Avro4S, and so on and so forth, that specializes on one of these bits of completely valueless code. For example, Codex is for serialization, but Scala check shapeless is for generating random data, and so on. But we end up with many different APIs that are not very easy to customize. And also, most of the time, it slows down compilation like a lot, especially if you use shapeless. And you get error messages that are not really friendly, to say the least. But that's not the real problem with compile-type derivation of this kind of behavior. The problem when you derive, especially serialization code or serialization objects at compile time, is that you are gluing together or coupling together the state of your code with the data your application will get in and out. And that can become very problematic. Let's take a look at a very, very simple distributed system with only 2 nodes. And these nodes communicate with one another, sending messages in JSON format. And in these messages, we have a field called name. But we decided in version 2 to rename that field and call it first name. So we deploy the version 2 on the node 0, but not on the node 1 yet, because we cannot shut down every node at the same time. And so all of a sudden, when the node 1 sends a message to the node 0, since the node 1 hasn't been updated yet, it sends a message with the field name. But node 0 is not able to understand that anymore because it awaits, it expects a field first name. So that's a problem of backward compatibility, right? And on the other way around, if the node 0 sends a new message to the node 1 with the first name instead of name, node 1 will not be able to read this message. It's a problem of forward compatibility. If we derive our serializers and deserializers at compile time, we will always end up with this kind of problems. And that's why we end up doing very, very nasty things like keeping all versions of our case classes in the code base just to be able to derive proper serializers and deserializers from them, for example. Or writing a whole bunch of manual serialization processes in order to keep backward and forward compatibility. That's not what we want. So that's what I call the evolution problem. And I suggest we solve it. But first, because all that, we want to do it with no boilerplate. We still want somehow to let the compiler help us doing that. But we just don't want to couple our serialization with the ADTs we have. So before solving the evolution problem, we need to find a way to get our serializers and deserializers for free. So this way, I sum it up in 3 requirements. We need a way to abstract over the structure of data. Because all this code we manually write or make the compiler derive for us, it has no business value because it's completely dependent on the structure of the data. So we need a way to abstract over the structure of data. That's what shapeless does. That's what Magnolia does, and so on. We need to have this abstraction available at runtime. Because if it's only there at compile time, we always have this backward-forward compatibility problem. And from this abstraction, we want to be able to derive a whole lot of operations, including serialization and deserialization. So this abstraction exists, and it's called a schema. A schema is basically a value that represents a type. But it's a value. It's accessible at runtime. So let's define schemas. So at the beginning of defining schemas, you need to remember why ADTs are called ADTs and what the A stands for. And the A stands for algebraic. And in fact, all these ADTs we can define are boiled down to a very, very, very simple algebra, which has only 3 constituents. The unit type, a binary sum, which is, for example, either, and a binary product, which is tuple2. And once you have that, you can represent any possible type, if you want. It's not very convenient, but it's doable. For example, if you want to represent a bit, which is only a 0 or 1, you can use either unit. A good way to convince yourselves that this kind of trick works is to try to count the inhabitants of the type you want to represent and the inhabitants of the representation you use. We know that there are only 2 different bits. So it's a type that is inhabited with 2 inhabitants. How many inhabitants has either unit? Well, there is only 1 unit. Okay? And either has 2 branches. It's a sum type. So the number of inhabitants of either AB is the sum of the inhabitants of A and the inhabitants of B. So either unit has 1 plus 1 equals 2 inhabitants. Same as bit. So we might be on the right track. And next, we can define a byte using the same ID and only the binary product. we can define these big, messy, nested pairs of bits. And if you count them, there are 8 of them. And we can count the inhabitants of these big types, by just multiplying, doing some multiplications, because the number of inhabitants of a product is the product of the number of inhabitants of each of its parts. So here we have 2 times 2 equals 4, 8, 16, 32, blah, 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 256. And we have as many of these types that we have different bytes. And so on and so forth. We can use the same trick to represent an option of A by simply saying an option is either a unit that will represent the none or A. And so we have A plus 1 inhabitants in that type. We could even represent recursive types using that same technique, but I won't get into it because it gets very nasty very, very quickly. But in the end, unit, a binary sum, and a binary product are all the things we need to be able to represent any possible algebraic data type. But of course, that wouldn't be very convenient. Remember how big was our representation of, oh, sorry, I missed the slide. How big it was for just a byte, so imagine bigger types. Oh yeah, I skipped this slide, but basically it says it works also for seal trait and case classes, because a case class is just a product and a seal trait is just a sum, right? So let's skip that. So of course that wouldn't be very convenient, and we need a few things to make it a little bit more usable. Basically we need a way to represent primitive types, so that we don't need to redefine bits as either units, and so on. We need sequences, we need records, because we need to have names on our fields, and unions, because we want to have names on our branches, right? But these are only convenience that we can add on top of this very, very simple algebra of unique sum and product. And in the end, at the end of the day, we can make all that thing work using isomorphisms. Because when I showed you how to count types, the idea behind is that if 2 types have the same number of inhabitants, therefore there must be an isomorphism between these 2 types. Yeah. And you can go both ways. So in the end, what we need to bind our concrete types, the type we love and use in our application, to this very cumbersome but very simple representation is an isomorphism. Because once you have a schema for A, if you have an isomorphism between A and B, therefore it's as if you had a schema for B. So for example, we could say the schema for a bit is the sum of unit and unit. But we want a schema for a Boolean, because that's what we use in our application. So what do? We just say, okay, there is an isomorphism between either unit, and Boolean. In fact, there are 2, but we just have to pick one. So we decide that left is true and right is false. And we just convert back and forth between this either unit, and a Boolean. And then we just say, okay, use that isomorphism on top of my schema for a bit, and you got a schema for a Boolean. And you can do that for any possible case class, for example. You use an isomorphism to explode your case class into a nested pairs that will be the same representation. All right, it's a little bit more complicated in SchemaZ, but that was the main idea. In fact, in SchemaZ, the schema is represented as a pattern functor. Are you familiar with recursion schemes? a little bit? Are you not at all familiar with recursion schemes? Like at all?
Sorry, what's the question with what?
Are you familiar with recursion schemes?
No, sorry.
Okay, no? All right. So recursion schemes is just a functional programming technique for managing recursion. And that's something we use extensively in SchemaZ. I won't go too deep on that. We can talk about it later. But the idea is to define your structure in such a way that it is a functor. And then all the processing you will be recursively doing on that functor becomes what we call an algebra, in which you only have to care about one layer of your structure. And the recursion going through, traversing the structure, it's carried out by the functor itself. It is very, very fast, but that's what you need to remember. And of course, because we want to be able to say, okay, this is a schema for this type, or this other type, we need to define our functor, pattern functor, in an higher kind. Because basically what we want to be able to do is to say, okay, this is the schema for a sum. The left part of this sum is a something of A. It talks about a type A. And this, the right spot, is something that talks about a B. And therefore, the sum we build on top of that is something that talks about an A or B. And so on and so forth for the product. So if you have heard about recursion schemes, this is the same thing but one kind higher, so it's slightly more complicated. Whenever you have a function in normal recursion schemes, here you need a natural transformation. But all in all, it's not that complicated. All right, so we have our schema, and the last thing we need is a way to derive all that code that has no business value from the schema automatically. And again, I will gloss over that very quickly. But what we want to derive is what we call operations on A. And an operation on A is just whatever looks like a function that either takes an A or returns an A or both. So for example, a JSON serializer of A is like a function that takes an A and returns some JSON. A deserializer is the reverse of that. A Scala check gen is a function that returns an A, takes no arguments and returns an A, or takes a random seed and returns an A, and so on and so forth. So these are the operations we want to derive for our schema of A. And most of the time we just say it's an f of A. And f will be JSON encoder, gen, or whatever. Okay? And the way we do that is, well, what it is to derive an operation is basically having a function that takes a schema of A for any A and returns an f of A. And if you squint hard enough, this is basically a natural transformation between a schema and an f. Right? Because we want to be able to write this derivation once and for all for every possible schema. So give me a schema for any type, I don't know the type. I will derive an f for that type I don't know from your schema. And how do we do that? By using the so-called recursion schemes technique, where basically what you do is you traverse the tree, you go to the leaves, you start building f of A's, f of something from the leaves. So for example, you have to say, if you have a bunch of primitive types like string, boolean, and number, you have to provide an f of string, an f of string, number, and an f of Boolean when you write the derivation. And then you climb up the tree, you fold the tree from the leaves by combining the intermediate results going up. So for example, when you get to a prod node, you have an f of A and an f of B, and you just need to combine them to have to get an f of the pair AB. And so on, going up. When you hit an isomorphism, you just map or contramap into your f, and so on. That's not the topic of the talk, so I'm glossing over that pretty quickly. And you can look very smart talking about higher kinded catamorphisms. It's very good. In a nightclub, perfect. So, back to what we wanted to talk about tonight. Solving the evolution problem. So, what we want is, first, and more importantly, always keep only one version of our ADT in our code base, because the less code, the less bugs, right? And we still want to have backward compatibility, so the new nodes can read the data from the old ones, and ideally forward compatibility. The old nodes can still read the data from the new ones. And if we look at this hard enough, it's just a matter of coming up with a specific reader. So this is the initial strategy we followed by when doing SchemaZ. So the idea is to define a set of operation or migration steps you can do between two versions of a type that will allow or guarantee that backward or forward compatibility is possible. So one typical example of a step is adding a field with a default value. When you add a field with a default value, you can prove that backward and forward compatibility are possible. If you just add a field without a default value, you will never have backward compatibility. You will have forward compatibility, but not the backward one, and so on. So first, we want to define this set of operations. Then we want to be able to define another schema, a schema for another version, starting from the current one, because that's the one we will always have in our code base, because we want only one version of our data classes in a code base. Then we want to use that in order to produce our alternative readers and maybe writers, what we call abrogating and downgrading schemas, and derive a reader for it. So first, the migration steps. It's just yet another algebraic data type. It's still to be built completely, but you can just add classes on top of that. So for example, here we have an add field, adding a field with a default value, renaming a field, and you can imagine a whole lot of other migration steps. Then you want to define the schemas, or what the old versions look like depending on the new one. So bear with me because it's a little backwards. What I want to be able to say is, so I am currently in version 2. I have my schema that has been manually defined or derived at compile time from the case class. I don't care. I have the schema. What I want to do is use that to define a schema for the previous versions. So I will have to move backwards. Oops, sorry. I will have to move backwards. I will need to say, okay, to obtain the version 2, what I did is adding this field age. And so this thing should give me a version 1 schema. And again, backwards to obtain version 1 from version 0, I did this operation. So this will give me the schema for version 0. Not exactly the schema for version 0, but a schema that will give me readers that will read version 0 data into my current version of the person class. That's important. So again, I move backwards from the current one. I define the old ones by saying what has changed, the changelog, basically. That's the changelog of my ADT, basically, but in reverse order. So for example, let's suppose that we have a person case class. In version 2, it has 3 fields: age, username, and email. And we say, okay, I have added the field age for version 2. Before that, it didn't exist. So if I want to be able to read the messages from the version 1, what I need to do is take the messages from version 1 and inject the default value of the new field in order to build a version 2 person. And that's what I do with this simple isomorphism. I say, okay, so pair string string is the representation of person v1. It had only 2 fields, username and email. And I want an isomorphism that goes from this old representation into the current version of person. So what do? When I get a pair string string, I inject a default value to the age, and I call the constructor of the person class. And on the other way around, I just forget one field and build a pair of just the 2 fields, username and email. So that's how we could do that manually. This is not exactly the schema for, this is not exactly the version of the schema that was in version 1, but it is a schema that represents the data produced by version 1 and bind it into the current version of the class person. Right? It's not exactly the same. But it does the trick. It does exactly what we want. And of course, all the trick, and I will get back to that later, is to be able to provide at the library level some way to get that ISO person vdo blah 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 from this. This is the user code, and this is somehow what the library should produce under the hood. I just pasted it here to show you how it works and that we could do that manually. And finally, when we get our alternative version 1 schema, we can use that as a regular schema and derive a reads or a writes from it. Or whatever we want. We can derive Scala check gen if we want, or whatever. So yeah, problem solved. Not quite. Actually, that was the, so this talk has evolved. I first gave it in March, before any of this was actually implemented in the library. And I've kept implementing the library and therefore changing the talk and added some slides. So, now that I have implemented the thing, or part of it, I can tell you about the problems I had. So first, the problem with this recursion scheme approach is that it's exactly its purpose. It hides the inner structure at the type level. So when you get a schema, you have absolutely no idea what structure it has at the type level. You can inspect its structure using pattern matching and so on, but you don't have enough type information to, for example, make sure that if you go down some path in the schema, you have a schema of int at the end of the path. And so therefore, you can plug an isomorphism from int to something else at that place. You don't have this kind of information at compile time, at the type level. And so it's not enough to build a robust and very useful library. So the first solution to this first problem was to introduce a phantom type, to gain back this type information we've lost by using recursion schemes. And we keep using recursion scheme because it makes everything else easier. But it makes it very, very difficult. So basically what we do is we add a phantom type that reflects the structure below, but it's purely phantom. It's like we tag stuff by using this kind of technique. And so now our schema type has two type parameters. This can be read like so. This is the schema of the type A using the representation R1, represented by R1. And a migration, if you think about it, is coming up with this kind of function. You still want to have a schema of A at the end. You're still talking about the same type, your current version of your ADT. But you want another representation. For example, give me a person from just a pair of string. Pair of string is the representation, roughly, and the A is person. And a migration is a function that takes your current version, your current schema, and gives you an alternative schema for another representation. So cool, looks like it solves the problem. But not at all. Turns out that it's not really a function you want, because this type depends on this one. It's a dependent type. It's a dependently typed problem. If you give me a schema, depending on the operation you want to do, the migration you want to apply, the end result, the representation, will be different because you've added a field or removed one or renamed something and so on. So every time, I cannot write this function without knowing enough on R1 in order to come up with R2. Fortunately, even though it's not strictly speaking a dependently typed language, Scala has a kind of a support for kind of dependent type programming, but it doesn't work. In this very instance, it doesn't work. And I banged my head against the wall for like 6 months because of that problem. At the end, I managed the compiler to tell me 1 is not equal to 1. So I suspect there is maybe some kind of bugs hiding somewhere in Scala C. But it's way beyond my power to just find them and even solve them. So I had to find a solution for that problem. And the solution is to just give up on generality. Because it turned out that this mechanism of inferring the new representation from the old one and the migration you apply, it works, but only if you do migration at the top level of your schema. So for example, if you have a schema for a record, you can add a field, remove a field, rename fields, and so on, but you cannot change the structure, the inner structure of the field. But as long as you define your schemas at top level, you'll be able to migrate them. But if you want to define, to migrate something inside your schema, so for example, imagine the person class had a field of type address, and you want to change something in the type address. With that technique, you need to define the schema for address at top level and reuse it when defining your person schema through function composition and so on. But in that case, that works. But again, it yields another problem, which is that if you force the user to split big schemas into very small ones, first, it makes everything a little bit more complicated. And again, the example of person and address, if I migrate address, that is, if I get a new version of the schema for address, I want this version to be used in my new version for the schema of person. And so I end up forcing my users to rewrite for each version all the schemas, which is exactly what I wanted to avoid. So again, and her head bangs against a wall a lot, but we found a solution. And I won't show you the code because it's a little bit scary, but the idea was to, instead of define schemas directly, just register a dependency graph of these schemas in the form of functions that takes parameters. And at the end of the world, when someone concretely needs a schema, you apply these functions until you get the schema. That way, you can change things, and the change will be propagated automatically when needed, without having the user to redefine everything every time. So how does it work? It's basically just a H-list that acts as a stack. It's a H-list of functions, and when you put something on top of the stack, you have access to whatever the functions that are already on the stack can produce. So for example, if I want to define or put on the stack my schema for person, there must already be a schema of address or a constructor of schema of address on the stack. But once I do that, if I migrate the schema for address, that is, I just post-compose a function on top of the function that I already have in my stack, returning a schema for address, then when I will execute the constructor of person, it will pick the right schema of address automatically without writing any code. And that's it. It's easier said than done. But so that's what it looks like. Currently in the current version of the library. So let's take a look at what this does. So here we are defining our current version of our data model. Of course, I've edited and skipped a few schemas, but the idea is we define this is the stack, right? This is the bottom of the stack, this is the top of the stack. So for example, I define a schema for user, saying it has two fields, name and active. Name is a string, active is a Boolean. I have this isomorphism between my pair string Boolean into user, and that's it. Then I can define, I don't know, a schema for person, for example, and person as a field of type user. And blah, blah, blah. So that's my current version. And I can stack a whole bunch of schemas as I need. And you see, it's just either a value directly or a function that takes a bunch of schemas and produces a scheme. That's it. And then, so this is the current version, version 1. But to get version 2, what I need to do is just saying, okay, take my current version, pick the function that returns the schema of user in that stack, and apply this migration to it. And that's it. And in the end, if I really need a schema for a type, because I want to derive something from that schema, for example, a serializer or the serializer, I just use the lookup method using the type. So this will give me a schema for person from the version 0, so it's person v0. So that's the actual user code in the library. And that's it. But remember, that's just the beginning, because here it's just a way to have evolution, but schemas can give you many, 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 many things for free. You can have random data generators. It's just accessible in SchemaZ doing that. You can have instances of EQ, or ordering, or, I don't know, show, or maybe something more fancier like generating forms and UIs just from the structure of your data, or Avro serializer and the serializer, or SQL queries and migrations based on the migrations you've defined in your Scala code. Or even crazier, you can go fully generic and say, after all, I don't even need my ADT anymore. All I need is my schema, and I just define operations in terms of schemas. I've already done that without SchemaZ, and that's something really, really powerful. So that's it. That was how SchemaZ tries to solve the evolution problem. It's still under work, under active development. Any contribution is very, very welcome. You can find my Twitter handle if you have any question, or the URL of the project. And before I go, I need to thank first John DeGoes, who kicked off the SchemaZ project more than 1 year ago, and Dominic Egger, who is my co-author and rubber duck for this project. And that's it. I'm Valentin. I'm working at 47 Degrees, and we are always hiring, so come talk to me about it if you're interested. Thank you.
Thank you very much. Thanks, Valentin. For me, it was a really interesting talk, and I have a question of my own, but before I shoot mine, I ask the audience whether there are questions.
Oh, yeah.
Hello. Yes, I have plenty of questions, but from the top of my head, this looks very similar, like, what is it called, the generic data generic libraries like Schema and so on. And so you said you already support use case like generating random instances of the data for beta testing. Do you also plan to support generating typeclass instances? If there's something on your mind, it's a totally different thing.
So from a schema, what you get is a typeclass instance. If you have a schema of A, I can use that schema and give you an egg of A, or a monoid of A, well, whatever. Maybe not monoid, but...
So functors, monoids, that's what you could generate from schema?
Sorry?
So functor or monoid instance, is that something you generate from schema? You said you can do EQ.
The A type must be of the kind star. So it cannot be a type constructor. We don't support that yet.
Okay.
But whatever, so EQ, show, JSON encoders and decoders, writers, etc., etc. But yeah, if your type is a IO-candidate type, it becomes much more difficult to us. Because from the back of my head, we would have to go ourselves yet one other kind higher, and I don't even know what's there up there. So But maybe I'm wrong. Maybe there would be a trick to use the current encoding to represent type constructors. I have no idea.
Thank you.
Anyone else? Any questions?
Thank you for the talk. It was very interesting. We struggle with this problem a lot, like with the backwards and forwards compatibility of the APIs. So I have a question. Do you consider this project still kind of like a research project, or would you not be afraid to put it into production?
So for the moment, there is nothing released yet. Right. It's still in a prototyping phase.
Oh, okay.
I intend to get out of that prototyping phase in the next few weeks, and I plan to have a first release before the end of the year.
Okay, cool, thank you.
But yeah, I still have no users, so I have no idea. Probably the instances we derive, are very, very not efficient. Because we are going through this intermediate representation in terms of tuples and isers. Maybe there is a way to avoid that, I don't know. Maybe it doesn't has such an impact on performance. I have no idea, because I have no users, because I have no release. But I will. There was another question.
Can I pass the mic to someone else? Any questions?
There was a migration from SchemaZ R1 A1 to ZR2 A2. You said that representation 2 is dependent on representation 1.
Can you repeat this? Where was it? This one?
No.
You mean the migration steps? No?
It was something like mathematical. Migration, representation 2 depends on representation 1.
Oh! Okay, here. Yeah. You want me to explain it again?
I don't think that R2 has to be dependent on R1.
Yeah. It means that the type R2, what type it is actually concretely, depends on what type there is here. So you cannot write this as a function directly, because you can know one but not the other, right? In Scala, you can write a function that is parametric in such. You have to know all the parameters at some point. What you can do is emulate this with abstract types and basically implicits. That's the way, for example, shapeless does seemingly dependently typed computations. But yeah, basically what that means is that you will have to compute, that's it, compute this R2 in function of R1. And you cannot know it beforehand. So that's the idea behind dependent types. And so Scala is not really meant to do these kind of things. We can do them, but partially. And in the end, it didn't work, what we tried to do. Because on top of that, what we wanted to infer here are type constructors and not just types. So types with a whole. And that's probably where it confuses Scala and we get this weird error message. Yep.
I think there are some additional features in Scala 3 or Dotty currently. I think they added a thing called match types or something like that, which behaves like a, you can define a function in the type level and inside you can match on the input which are types, so you can do that. Have you experimented with Dotty or the Dotty features?
Not yet, but, and I've not experimented with Dotty at all yet. But yeah, probably there will be features that will make this kind of things slightly easier, or at least doable in the next version. We'll see. Maybe, maybe not, but yeah, it's probably promising for this kind of things, because it's still a very specific use case we have. It's not the fully fledged dependent types. So. Yeah.
I had a hard time getting my head around the H-list. How does one arrive to some middle version of your schema, representing it like the way you did it with the stack? I have a hard time getting the process. How do you arrive to some middle version of your schema?
Okay. Maybe I was a little bit fast on that side. So the idea is, so forget about H-list. It's just an implementation detail. But imagine you have a stack of functions, right? The functions at the bottom of the stack, they will take no parameters because there is nothing yet produced to feed them parameters. So this will be your smallest schemas, right? The schemas that depend on no other schemas. You put that at the bottom of the stack. And then on top of the stack, you can put a function that takes parameters as long as these parameters are produced by some function that are already in the stack. So for example, if you have a schema for, say, person, and this schema needs a schema for address and a schema for company, for example, you cannot put this function that will take a schema for address and a schema for company and return a schema of person. You cannot put that function on the stack unless there's already on the stack one function that returns a schema for address and one function that returns a schema for company, and so on. In that way, what you have is some kind of dependency graph rather than a stack. But the cool thing is now, if you access one element of the stack without touching anything else, and you just post-compose something, because this is a function, you post-compose another function, for example, a migration, you can have this change be reflected or propagated to everything that is up the stack. And that way, you apply the migration to address, and it will be reflected in person as well. Makes more sense?
Just a follow-up. Is it how is it done that you don't repeat yourself in a way that you said you don't compute or recompute the versions every time? So is that the H-list representation encodes the whole world that you can do?
So do I have it somewhere? I didn't want to show the code, but what? Sorry. Nope. Anyway. I have broken my Emacs, apparently. Okay. Maybe the code won't help at all, but
Is that the implementation or usage of?
no, this is the implementation. What I can show you the usage. You're right. It's will be probably more clear. So here. So, for example, this is what you do to use the migration. I must show you something else. This one. So this is the big data model for our tests. So this is the stack, right? The bottom is at the top, and the top is at the bottom, but you get it. So for example, here, I put on my stack a function that takes a schema of user and a schema of admin, and returns a schema of role, which is the CL trait on top of user and admin. And I can do that only because below it, on the stack, I already have a schema for user and a schema for admin. Right? If I put this here, it doesn't compile. And so on. Person uses, which one it is? Person uses a role, and so it must come after it. Right? And once that is done, I can go and do some migrations. For example, here, let me make that a little bit bigger and put it at the. So here what I say is I take my current version, so the big things produced by this. I grab the function that returns a schema of person, and I say apply this migration to it. And this is, of course, not a very good example because I should have done that on something that is below, so for example, user, but you see the idea. If I had other schemas depending on this one in my graph, they would be automatically in version 0 updated with that migration. And what I do, once I've built a version, I just need to look it up for that's it, for a schema. Just look up. And the magic is done at the lookup, actually. Lazily, at the first lookup, what I do is I go through the stack, I apply the functions that gives me schemas so that I can put them as parameters to other functions and so on until I've built all the schemas, all the values. Make more sense? Cool.
Yeah. Hi, maybe one more question.
Sorry?
Maybe can you go back? Can you, yeah. Line 52, I don't really see how can you make sure that the types match here, that the name is actually a string. Is it like a runtime thing only, or
no? So
there's some magic that I don't see.
This is a little trickery. It's shapeless. I intend to in Scala 2.13 we have singleton types, so we can avoid shapeless altogether. But the idea is to say in your schema the names of the field must have a singleton type, so that we can verify at compile time that your migrations are correct.
Thanks.
Yeah, sorry for such a question, but I'm lost where on the right pane, there's this value called current at the top. Is that like the newer version of the schema than the V1, sorry, V0, or which is, what I'm confused about is the direction. What is the old, what is the new?
Current is the newest. It's the current state of your code.
Okay. And the trick is that you're defining the older versions in terms of the newer ones.
Exactly.
Okay,
because at the end, when you will read a message from the outside world, you still want to build things in your current state.
Or because you have your internal,
your
model
AT.
in the newest, in the terms of the newest data class. Yeah, okay.
Sorry, this is going to be the last one, I hope. So if you have like 5 versions of the schemas, right? You have the current and then the current -1, -2, -3, -4. And you receive some message from the outside world. How do you know which version you should like start from?
This is up to you. SchemaZ doesn't have an opinion on how you do that. You can add metadata, you can use different channels, version channels. That's up to you. But once you know what version to use, you can pick the right one to get it.
Okay, great, thank you.
Thank you very much. Are there any other questions before we wrap it up? Okay, thanks.
Thank you.
Yeah, one more, the very last question.